All right, so let's see here. So this is the what we call the locally linear. Okay, so 8 here is a vector. It's a vector. See, this is the that angle. Okay. Sometimes we write as this one. If we write something like this, this is coordinate. Sometimes we write this as this one. This is as a vector. Okay. So the thing is, x and y is the end point of the vector xy. So this is the end point. Okay, you can remember the last chapter on vectors. Okay. Okay. So then let's see what this locally linear means. Okay. So let me rewrite this one and make some simplifications. Okay. So this equals to f of AB. Okay. And plus h1 times, this is the partial derivative. Oh, let me rewrite this as partial derivative. df dx computed at AB plus h2 times df dy computed at AB plus and h2 epsilon 2 there. Okay, so let me rewrite this on as, okay, especially this one. Right, so this is factor h1, h2 dot product with x comma df dy computed at AB. Okay. Plus dot this one. Okay, this is also the same thing. Dot there. Okay. And we have a new thing here. This one. Okay, so this is a vector. Each component is a partial derivatives. Okay, this is called a gradient vector, gradient of f. So gradient of f, the notation is this. This notation symbol here is called nabla. So nabla f meaning the gradient. Okay, this h. So you see the analogy with the with, let's say the analogy, one variable This is f of a plus h times f prime of a. Okay, so what's the analogy here? Okay, this and this is okay. So in one variable we call it f prime. Here we have this vector. Okay, this one. So basically, locally linear means that you can somehow approximate this using this times this one. But what is actually this one? Is this actually the equation for tangent plane? I see. Uh, so it's all right. So equation for tangent plane. Actually, this is part of the things we had in the last chapter. Okay, let's see if you have a surface. Okay, and so this is the point. You have this is the uh, say this is x north, so x a is constant, and you have also a curve here. This is a f of say x vary while the b constant. Okay, and recall at this point here. So uh, here we have this one, and so this one x varies. So we can compute this one. So this is the FD x at y equals b. This is the slope of tangent of f x comma b. And this one y equals 3. This is the FDY, the FDX when x equals a. This is AB. This is not y equals b, but AB. This is slope of tangent line for f a. Okay. So now as a vector, we say this is a, we call it, say this is 1 df dx. And this one as a vector, this is 1 df dy. Why 1 because it's going y 1 and then it's going up like this. Okay, and if you cross this equation for line containing two vectors, if you cross this out, what you get here. For example, if you cross, you get this one here. There, the normal factor. Recall from last chapter, the normal should be computed by uh, notice not completely normal, but somehow say this is T, this is W. Okay, so the normal should be W cross V. Okay, so what you get there? Uh, W cross V. What is that thing? So this is I, J, K. W is 1, 1, df, dy. V is 1, 1, df, dx. There. Okay, let's compute this one. So the I is df, dx minus df, dy. I think I was wrong. I think I was wrong in this one here. Sorry. Right. Let me write this one. It's not 1, 1. All right. So this goes along because this, let's see, x differ by the y is fixed. So y is fixed, the direction is 0, this is 1. Okay. And this one, the x is fixed. So no difference, this is y. Okay, so we get this one. Okay, that's 0. 0. Okay. So let's now do this one. So the I component is 1 times df dx minus 0 times df dy. So just df dx. Okay. So the j is 1 times df dy minus 0. So just j. And the k is 0, 0 minus 1. Okay. Okay, so let's see. So negative 1. Okay. Okay. So this is equations as a factor. This is df dx, df dy minus 1 common. Okay. And recall that the plane with the with this normal, having normal this vector is the equation for a plane with normal df dx, df dy -1 is the following. So this is the f dx, x minus there. So sorry, this is x minus a, okay, plus you see the components of the normal is the actually coefficient for the plane. AB computed x a y minus b minus, okay, the f a equals 0. Okay, so what is this? Let's rewrite this one. Okay, so put this b here, move this one. Oh, okay. Should say that. Let's see here. So what we get is that z equals, what the rest is, minus minus become plus. Okay, plus this one here, df dx a comma b, right? Plus df dy. That's why I prefer not to confuse with the multiplications. This is computed at a comma b plus df dy. Okay, so this is the equations, and you can further rewrite this as let's see as this factor here. This factor, so df dx, df dy computed at ab dot x minus a y minus b. There we go. And you can see this is because this is the gradient. AB dot here x minus a minus b. Okay, so this is nothing but, let me move this. Again, to the definition of here, locally linear. Okay, so in this definition of locally linear, it turns out that the this one here is actually the equation for the tangent plane. This is the error. Okay, so this is tangent plane. This is the error. Okay, so this justifies our definition of a differentiability, means that f two variables is differentiable if it can be approximated by tangent planes. Well, sufficiently good. What is sufficiently good? The error is much smaller than the error in xy. Okay, so it turns out that we can adapt these definitions to any number of variables. Okay. All right, so that's uh, about differentiability. So let's do some more computations. Let's take a break for 5 minutes. Let's take a short break. All right. Okay. And so that we, okay. All right. So that it is. So in factor form, this locally linear thing is can be written as this one here. Okay. And so this is how we define differentiability. Function f is differentiable at the point p, p is in factor form, if it is locally linear at p. It is differentiable in open set if it is differentiable at every point. Okay. So this is rather complicated definition actually. So but we only use this thing here. If f continues as partial derivative, continuous partial derivative f sub x partial s sub y on this containing the points, then f is differentiable. Okay. So this is the important thing. Let me just copy this one. We'll just use this. We won't uh, use the definitions. All right. So thing is this one. Okay. And the thing is, why this example is not differentiable? If we go back to this one here, the beginning, why this is not differentiable? Let's see here. In this case, the partial derivative exists at this point. Okay. So partial derivative exists at 0, but 0 only. This exists only at 0. That's the problem. It's not defined on the some set containing the 0. 0. Okay. So only at this point. So that's the reason why we cannot use this theorem. Okay. So if it exists, partial derivative, but only at the point. So not on a disk containing AB. Okay, so this is all right. So our case is always differentiable for two variables. Okay, so let's do some more problems now. That's the this is our case. Okay. So we won't go to non-differentiability for two variables. Okay. Let's do some. All right. So let's the example here. Let's find a tangent plane. First, just look at the example here on the textbook. Okay, so find given an f here, given an f, uh, differentiable everywhere. Okay, why? Because let me rewrite this. Um, let's look in detail. Okay. Show that this function is differentiable everywhere and calculate its gradient. All right, so let's rewrite this one. Is x e to the y plus x squared y. Okay, so let's check the partial derivative. So the f dx is, let's see, just e to the y, just and to xy. Okay, while the f dy is respect to y, so e to the y, same e to the y, so x e to the y and plus x squared. Okay, so now both are nice functions. So that's the differentiable. Okay, so here both exist. So just both are defined and continuous for any x and y. Okay, so then this satisfies the assumption or hypothesis of theorem A. Is it theorem A? Yes, theorem A is satisfied. Therefore, f is differentiable everywhere. Okay. And what's the next questions? Calculate its gradient. Well, gradient is just gradient, it's just df dx, df dy. So factor. Just rewriting this e to the y, y, x e to the y plus x squared. Okay. So the equations for the for the tangent plane of f at the point 2, 0. Okay, so let's compute this one first. Just plug in 2, 0 here. So this is e to the y, so e to the 1, so that's 1. E to the 0. It is that's 0. Right, so this 1. And then here you have like in x2, y0. So this is 2 plus 4, 6. Okay. All right. So equation for the tangent plane is that z equals half of 2, 0. Well, we haven't computed it. Plus, this is the 1 times x minus 2 plus 6 times y minus f20. If you plug into f20, that is 1, 0, 2, 2. Oh, sorry, I uh, should plug into here to 0. So you plug in 2, 0, 2, plus 3, oh, that's 0. Okay. Uh, 6. That's equation for tangent plane. Choose 0. All right, any questions? Okay, so this only finds the gradient vector. So just compute the derivative. So these are 3 variables. So check the partial derivative with respect to x sine z plus 2xy. Okay, df dy with respect to y. So just x times z respect to y, only this one derivative. So x square, and with respect to z is just x cosine z. Plugged in 1, 2, 0. Okay. Here's the factor notation, ijk. And to 1, that is 0. To 1, this is 2. Sorry. 2 times 2 is 4. Where this is another 1. And this is, let's see, 1 times cosine 0 is 1. So 4, 1, 1. Okay, so this is the uh, property of the gradient. If you take a gradient of a sum, and it's just the sum of the gradient, each gradient, And also if the function is multiplied by a factor, is constant multiple factor, and then you can factor the constant. And this is the product rule. Okay, so that's easy. Again, as in the one variables, differentiability means continuity. All right. So that's all uh, uh, for the differentiability. We won't talk much about this one. We'll use that. Okay. So now what we have is what we call the gradient directional derivative. Okay. All right. Okay. So again, if you have we have a surface, and this is the axis. So if you look at this point, so this is AB. Okay. There. Okay. So you have the partial derivative. Partial derivative is a slope, actually. Not the blue one, sorry. Should be clearly red. Okay. And slope of this direction is the FDX. And slope in this direction okay. So derivatives meaning slope anyway. So the only thing is that when you're in one variable, meaning slope is that, well, you're what is slope? Slope is slope as you going from left to right. So there's only way from left to right or from right to left, either way. But when you're standing on standing on a mountain, not on a mountain actually, on a side of a mountain, then you see that the slope are different from, maybe different, any direction you see you're facing. Okay. So here, for example, your mountain. So you're standing here, or a hill, actually. You're standing here, and you start looking around 360 degrees. So in this direction, you're going down. Here you're going down. Here you're going down. Here, well, maybe not, because here seems that you don't go down or go up. But here, go up. Okay, seems that the slope varies as you look in different directions. Okay. The thing here is in our case, so dy dx and df dx and df dy is only two directions, two of the directions. Okay. So this one in let's see, x direction, this one in y directions. So the question is, what's the slope of other directions? So the question here. In say in direction of v, for example. Okay, so this is what we call directional derivative. Okay, so let p be a unit vector. So, directional derivative f is um, at say AB. Then we call the directional derivative in of v at AB is this one here. That is v dot gradient of f at AB. Okay, so this is what we call the slope of the tangent line. Sorry, for tangent plane at AB in the direction of v. Okay. So what we have is that note is the slope of tangent. This is x direction. Okay. So x direction, this is direction. V equals 0. Sorry. And the FDY, this is in y directions. So V equals 0, 1. Okay. Just one example. Now let's pick up There we go. Okay, just point out here. Let's see. We're given an f here. 4x squared minus xy plus 3y squared. This. Find directional derivative of f at this point, 2 minus 1, in the direction of this vector a. Okay, but first, normalize factor a as directional factor, because a directional factor should be normal, has length 1. This has length 5. Okay, so divide by its length. So u is in direction a. The unit factor is divided by 5, so it is 4/5 and 3/5. So this is our directional derivative. Sorry, directions u. Compute now the partial derivative x. Y is this? And thus a plug in 2 comma negative 1. 20. Okay, so the directional derivative with respect to u. Okay, so this notation also, we use this one. So this is u. U now is 4/5, 3/5. Okay, times 17 negative 8. That's the gradient. So that's what we get. Right, so that's the slope of f in u directions. Okay, questions? All right, so we'll stop here. Let's finish this one tomorrow, directional derivative, and we'll continue with the next is just a couple of bit more examples of this directional derivative examples, and the next on the chain rule. Okay, questions? Stop the record. All right. If not, then let's see.